Welcome to a screencast on Le Chatelier's principle. Back in 1884, the French chemist Henri Le Chatelier came up with the following statement. Any system in stable chemical equilibrium subjected to the influence of an external cause which tends to change either its temperature or its condensation, which is pressure, concentration, number of molecules in unit volume, either as a whole or as some of its parts, can only undergo such internal modifications as would, if produced alone, bring about a change of temperature or of condensation of opposite sign to that resulting from the external cause. Well, that's kind of a mouthful, and this was a fairly cumbersome statement, and after several iterations, Le Chatelier boiled his principle down to, this is our sort of modern version of what's called Le Chatelier's principle. When a stress is applied to a system that's in dynamic chemical equilibrium, the system tends to adjust to minimize or reduce the effect of the stress. And it's a very simple and powerful principle, and it's maybe best seen by example to certain circumstances, and then we'll apply it to very specific situations. So here's your classic equilibrium, the Haber process making nitrogen and hydrogen into ammonia and H3. So this is our equilibrium system we'll use as an example. And if we were to have some nitrogen, hydrogen, and ammonia in equilibrium at a given temperature, and to that system we added a reactant, either nitrogen or hydrogen, the reaction would tend to react in the direction that reduced or minimized the added stress. So if the stress is adding N2 and H2, the system wants to reduce the added N2 or H2, and by reacting to the right, that uses up some of the added N2 or H2. And so in general, if you add a reactant to a system that's in equilibrium, the reaction tends to, we'd say, go to the right, forms quote-unquote products. Now, if we were to have a system in equilibrium and we added product, in this case we add ammonia, the stress is added product. The system wants to reduce the stress of added product, and reducing the stress of added product means that the product gets used up, or the reaction, we would say, goes to the left and makes more quote-unquote reactants. Now, we could have a system in equilibrium, and instead of adding reactant or product, we could remove reactant or product. Well, now removing nitrogen or hydrogen, the reactant, now the stress is there's less of the substance. The system is going to want to minimize the stress or counteract that stress, so it makes more of the reactant, and so the reaction is going to go to the left to make more of what was taken away. And of course, if we were to remove some product, in this case NH3, the stress is taking away NH3. The system wants to then make more NH3, and so the reaction would go to the right to make more NH3. Now, if we have a gaseous reaction mixture and we compress it, we can see or think about what happens, again, by looking at the nitrogen, hydrogen, ammonia relation or equilibrium. So here we have a container of nitrogen, hydrogen, and ammonia in equilibrium. Compressing the reaction mixture means we squish down the volume, and if we decrease the volume, that has the effect of increasing the pressure. And increasing the pressure, well, that's the stress. So the system wants to counteract the stress by decreasing the pressure, and that means if there's a way for the system to make less gas molecules, then it does so. And in the case of nitrogen, hydrogen, and ammonia equilibrium, remember that the reaction equation is 1N2 reacts with 3 H2s, so that's 4 total molecules, to make 2NH3, so that's 2 molecules. So going to the right, making ammonia, takes 4 molecules, turns them into 2 molecules. That makes less molecules, and that's counteracting the added stress of increased pressure due to decreased volume. Now, if we have a gaseous mixture in equilibrium, again, nitrogen, hydrogen, and ammonia here, and we added an inert gas, In this case, even though the inert gas contributes to the overall pressure, it doesn't change the partial pressure of the hydrogen, the nitrogen, and the ammonia, and those are the things that matter in the equilibrium. So you didn't actually stress the system. You didn't change the pressures of any of the substances, reactants, or products in the system, so the inert gas doesn't react with anything, and because of that, the system tends to not change. We didn't actually stress the system itself. And then if we look at effects of temperature change on a system, if we raise the temperature of an exothermic reaction and we want to think about or figure out what happens, remember that an exothermic reaction, so here a generic reaction A plus B makes C plus D, if it's exothermic, heat is a product of the reaction. And so our system is A plus B makes C plus D plus heat, and raising the temperature means you're adding heat to the overall system. That's adding essentially a product. And so if we add a product, the system wants to use up product and make reactant. So the reaction goes to the left and it favors formation of reactants. And then, of course, if we lower the temperature of an exothermic reaction, well, now the stress is we're removing heat from this system. Removing heat is removing a product. Therefore, the system wants to make more product, which means it forms product, goes to the right, and the reaction, if it's exothermic and we lower the temperature, it favors formation of products. And, of course, if we have an endothermic process and we look at its temperature change and effect of that on the system, endothermic process have heat as a reactant, so A plus B plus heat makes C plus D. And now if we raise the temperature of an endothermic reaction, we're adding heat to this system. The stress is added heat. Heat is a reactant, so the system wants to use up the heat, use up the added reactant, and form products. And then, of course, the remaining thing to consider is if we lower the temperature of an endothermic reaction, and now the stress is removing heat or removing reactant, and if we remove reactant, the system wants to make more reactant, so this reaction will go to the left, making more reactant or favoring formation of reactant. And that is pretty much it. That's the gist of Le Chatelier's principle and how it behaves.